Hi, my name is Andrei Konovalov. I'm a PhD student in Moscow working with Chris Braff. My research is mainly related to study of invariance of K-linear stable infinity carries or K-linear study of invariance of DG carries over K. These DG carries come from a lot of sources. For example, some of them come from symplectic geometry, some of them come from topology, some of them come from algebraic geometry. But the point is that all of them can be treated in a unified way, and sometimes one can even deduce the statements about one digit carries from the statements about the other. And actually, by an invariant of digit carries, I mean just a functor to the carry of spectra or to the carry of complex vector spaces. And the main example of this would be a periodic static homology, which, depending on the characteristic, can possess different structures. And the main case of interest for today would be the field of complex numbers. In this case, one has intuition coming from Hodge theory. Let me remind that when one has a smooth projective variety of complex numbers, one has a Hodge-Durand generation, which goes from the Delbourg homology, which comes from the spectral sequence going from the Delbourg homology to jump homology groups. It degenerates on the first page given a decomposition like this. And one can also look at the basic homology, singular homology of the underlying topological space with real coefficients or integral coefficients, and they would give real or vector or integer structures on the RAM homology. Actually, the real structure is equivalent to given a conjugation like this, and this conjugation actually flips HPQ pieces with HQP pieces. The question of interest is if one can generalize this picture to the non-commutative context, to the context of DG categories. And an example of a statement like this is the theorem of Kaledian, that the spectral sequence from Hodge homology to periodic static homology generates at the second page. And this should be thought of as an analog of Hodge-Durand degeneration, because due to HKR type statements, actually two periodized jump homology are equivalent to periodic static homology of GK of type perf X. And analogously statement holds for Hodge homology. Since then, two shorter proofs of this statement have appeared. One belongs to Kilmetri and uses some cyclotomic spectral theory, and another belongs to Dim Kaledian, Kirill Magitson, and myself. And it uses an observation that every G carry which is smooth and proper over C can be lifted to some smooth and proper G carry of some formally smooth infinity ring. This theorem of Kaledian gives a non-canonical Hodge composition like this, and there is a question of constructive conservation boundary if there is a functorial rational structure HP. In particular, it would follow that this composition is canonical. And there are some other statements and possible applications. And let me note that in the geometric case, one has such a rational structure. One can take either two periodized basic homology or a rational topological theory as such a rational structure. Anthony Blank has constructed a functor, a topological theory called topological theory due to this motivation, such that on schemes it's equivalent to the classical topological theory, and there is a factorization like this. So one has a map from topological theory to periodic static homology called topological chain character, and it factorizes the trace canonical classical trace map. Okay, and the main theorem of me is that the complexified topological chain character is actually an equivalence in several cases of interest. One of them is let me remind first that every smooth and proper G carry is equivalent to G carry of type perf B, where B is just smooth and proper GGA. So One of my example is that one can look at connected J, which is proper and even not necessarily smooth, or more generally every connected J such that its H0 is some nilpotent extension of some commutative finite type algebra over C, maybe non-commutative nilpotent extension. Then one has an equivalence like this. Another example of interest comes from derived algebraic geometry. One can look at nice derived algebraic spaces, and then one has equivalence like this. So this was slightly generalized by Alman and Susnila in 21st year recently. Another third case of interest, which is related actually to the another case of interest given by reactive carriers, is the infinite carrier of infinite carriers like which look like local systems of spaces over M with some condition on the fundamental group. In this case, one again has invariants like this, but of course the main question is what is the condition. Let me say that some condition should be imposed, because if one considers pi 1 equivalent to the infinitely generated free commutative group, the free commutative group on the infinite number of generators, then topological chain character is not an equivalence. But still, in a lot of reasonable cases, one has an equivalence like this. Let me not state accurately what this is, but let me say that if the Farrell-Jones conjecture in the weak form is satisfied for the group, and Bulgarian conjecture is satisfied for the group, then the largest conjecture would follow. Actually, one can look at the opposite direction, and if one finds a group for which Bulgarian conjecture is satisfied but not the largest conjecture, then the Farrell-Jones conjecture would be also false for this group. So this can be thought of as a possible way to find some counterexamples to the Farrell-Jones conjecture. In general, topological theory is defined using the generalization factor. So one looks at, we should be sort of just, one has a functor and one looks at the underlying set of complex points. In particular, when one has a unidirectional functor, it's exactly the suspension spectrum of the space of complex points of an affine scheme. And it turns out that realization of the functor which assigns to an affine scheme its algebraic K-theory is just the connective truncation of topological K-theory. So in general, one defines same topological K-theory like this, and topological K-theory by inverting the Bodge element. And the other theorem of me is that this same topological theory is actually derived from invariant, means that for any map of connected digital algebras, which is a nilpotent extension on H0, this map of on topological K-theory would be an equivalence. My proof is based on computation of realization of Hochschild type invariance and the usage of Goodway theorem, which can be actually avoided using modern machinery of Lantama. I have several related products. One of them is motivated by some classical picture, and the question of interest is when one has a family of GG categories over some base, where B is just some nice scheme, one hopes that the HP and topological theory would possess structures of local systems, and this would be a map of local systems. I checked this theorem on several cases of interest, and I'm working on proving this in sufficient generality. In particular, one could use such types of statements in order to deduce some statements about general fiber from some statements of one single fiber, where everything is simple. Thank you for your time.